Let's continue working examples for the absolute ratio test. Here's another one. It's a positive test. We don't have any alternating terms in here. But again, we can continue using the absolute ratio test. It won't hurt a thing. So the nth term, we can clearly see, is here. The n plus first term, this is the first time in the denominator here where you're going to begin to see a little bit of how important it is to put parentheses around where n used to be. I've got other problems that we'll see where it's much more important. But this cleans up really nicely to just the quantity n plus 2 factorial. So let's put that in our limit. The limit is n approaches infinity. And we will put 3 to the n times 3 in our numerator there. We will also go ahead and factor the quantity n plus 2 factorial and recognize that just like n plus 1 factorial is n plus 1 times n factorial, n plus 2 factorial is going to be n plus 2 times n plus 1 times n minus 1, and so forth. And we can see right here that n plus 2 factorial is n plus 2 times n plus 1 factorial. So it's perfectly fine for us to rewrite that in this way. And then we're going to just write the reciprocal of a sub n. So you can see that this, more than likely, once you get comfortable with your factorials and exponential functions and such, this is probably right where you'll go to. And you'll see that evaluating this limit won't be that difficult once you do all that algebra right up front. So this is 3 over n plus 2. As n goes to infinity, this limit is going to 0. Remember, that is rho. Rho is less than 1. This series converges by the absolute ratio test. So now let's work an example or two on an alternating series. You can see here we have it with the alternating term written out front and then the positive portion of the term right there. So as far as a sub n and a sub n plus 1 are concerned, all I'm really interested in is the positive portion of this alternating series, because that's all I'm going to plug into the absolute ratio test. So there you can see there's a sub n plus 1 and a sub n. The limit as n approaches infinity, I'll have 3 to the n times 3 over n plus 1 times n factorial. That will be multiplied by the reciprocal of a sub n. And I can cancel common terms. And this is the limit as n approaches 3 over n plus 1. Again, that's 0. Remember, that's rho. Anytime rho is less than 1, your series converges, and you're running the absolute ratio test. Now, if they ask us, because this is an alternating series, if they ask us, does this converge absolutely or does it converge conditionally? Remember when we talked about the absolute ratio test, this proves absolute convergence. So this alternating series converges, and it converges absolutely because we're running the absolute ratio test. Notice I did not put that alternating term in the absolute ratio test at all. When students do that, they wind up confusing themselves. I see this every year. We go for a little bit where a student will forget that they're not supposed to put the alternating term in there. And so this is what I'll see. I'll see, actually that should be n plus 2, n plus 1, and then we would have n plus 1 and n factorial and 3 to the n down here. So that's what it would look like. And students do this and they don't know how to clean it up. Or they might say, okay, that's negative 1 to the n times negative 1 squared, and I'm just going to work on what's in my box there, over negative 1 to the n times negative 1 to the 1. Okay, those cancel, and one of those cancels, so this is just negative 1. Recognize that inside those absolute value marks, it does not matter whether that alternating term turns out to be negative or turns out to be positive for the nth term or the n plus first term. So don't even put it in your absolute ratio test. That's the power of the absolute ratio test, is it doesn't matter what the alternating term is doing. So don't fall into this trap. That's the number one error that I see that students make, and then they get all bogged down just in that, get confused, and walk away from the part of the limit that they are used to dealing with because the negative ones confuse them. They don't remember using them when we did them on homework because we don't. But then they get in a test situation and freak themselves out. All right, so test for convergence or divergence. Here, this is an alternating series. This is an alternating term. When n equals 1, the sine of pi over 2 times 1 is 1. When n equals 2, the sine of pi over 2 times 2 equals the sine of pi, which is 0. When n equals 3, the sine of pi over 2 times 3 is the sine of 3 pi over 2. So not only is it an alternating series, it's a series where every other term has a coefficient of 0. So this is an alternating series, but we can still use the absolute ratio test to find out whether it's convergent or divergent. This is the first time where I truly have an example that you can see how important it is that you put a parentheses around where n used to be. Because e to the 2n plus 1 does not equal e to the 2 times the quantity n plus 1. That 2 distributes. If this was a multiple choice question, that would be the number one distractor. That would be a choice, and it would be the number one distractor. So this is a perfect illustration of why it's so important that everywhere that you had an n, put a parentheses, and then put an n plus 1. So there's the n plus first term. So let's come down here, plop all of this in the limit. We have e to the 2n times e squared. Do you see this numerator is e to the 2n plus 2? So that's how that would be written. This is then multiplied by n to the n. This is all over e to the 2n times n plus 1 to the n plus 1. So, is it true? This would be, this is obvious. We'll go ahead and get rid of that. Here's our big question. Does that act like 1? Are those two things going to cancel each other out? Well, inside the limit, those are indeterminate forms. This is infinity to infinity, and this is infinity to infinity. So the question is, does infinity raised to the infinity power over infinity raised to the infinity power, does that equal 1? Well, infinity raised to the infinity power is just infinity. These two things, that's not indeterminate. This is not indeterminate. That's infinity. But together in a ratio, those two things are in indeterminate form. We are inside of a limit. We know how to deal with an indeterminate form inside of a limit. Now, this term, as far as n is concerned, is a constant. We could pop that out front. That's not an issue. So now I have n to the n over n plus 1 to the n plus 1. That is infinity over infinity. We're not sure what that's doing, and we're going to have to explore that a little bit. Now, I will say this, once we explore it, if you can remember what happens here, and this shows up ever again in any of your absolute ratio work, then you can just use that. We can use L'Hopital's, but I want you to think about what the derivative of n to the n is going to look like. I'm going to pick up another color so you can follow me. That's one of those undefined functions. Remember us doing that? This is not a power function, so I can't use the power rule. This is not an exponential function, so I can't use the exponential rule. I have to come outside of the limit. I'm going to introduce natural log to both sides because now I can change this indeterminate form using the property of the logarithm into a product. So that's what that's going to look like. But I have to remember that I'm taking the limit now of the natural log of my function. So I'm going to come back over here. I'll stay with the green. And e squared is just a constant. I'm going to put things back in terms of n. And now in my numerator, I have n times the natural log of n. And in my denominator, I have n plus 1 times the natural log of n plus 1. So there's what my limit looks like now. And I can tell you that algebraically, that is acting like 1. I can also tell you algebraically, that is acting like 1. So this limit, e squared times the limit as n approaches infinity, it's acting like 1. But remember, that's not rho. I haven't found rho yet. This is the natural log of y equals 1. So now I'm going to have to raise both sides to get back to y, which was where I started. And y is e. So this limit, if I'll come right back to where I was, I'm trying to watch my time if it looks like I've lost my mind here. So I have e squared times the limit as n approaches infinity of n to the n over n plus 1 to the n plus 1, and we could take absolute values of that, is e squared times e. That's e cubed. So rho is e cubed. That's greater than 1. This series diverges. And diverges, I'm not going to take time to write it, by the absolute ratio test. So all of our limit work, everything we know about evaluating limits, is going to come into play here. Now, we have a couple more things. I have a whole summary that I want you to put in your notes. So there will be an additional video, so look for that.